always good to review multi-step synthesis, and we blaze through it fairly quickly. So there's some subtleties I want to go over. And when you look at this, alkyl halide and aluminum chloride, this looks like the fetal craft alkylation. Then I look at this and I see that I'm going to put a nitro group on here, and an alkyl group is an ortho-para director. Then the next thing that occurs is we oxidize the side chain. So notice here we have the same reagents but in a slightly different order. So we're going to put an alkyl group on the benzene ring, and then we're going to oxidize that. And we got benzoic acid. And what type of director is carboxylic acid? So I was grading the exam, and one question was, show how you could prepare something from something. And a few of you got all the reagents, but not necessarily in the right order to get the desired product. So that's one reason I wanted to go over this a little bit. Here we get the meta, here we get the ortho or para. So we do extractions in the fall, and I always feel kind of bad because we haven't gone over a lot of maybe acid-based chemistry extractions, but we went over it well enough. When I was editing the video, I saw that I said, oh, you could have this in ether and you could add some water and take away the neutral things. That's something I really wouldn't want to do with an amine, because an amine will react with water, as we saw in that previous slide. Ammonia reacts with water and makes ammonium hydroxide, and there's some equilibrium there, and you'd lose some into the aqueous phase. Once I put this in ether, I'd either want to hit it with basic water or acetic water to force one of two things to happen. And that's probably true for any acid-base extractant. If you're extracting a weak acid, you're either going to make it real acidic or real basic. Same thing for weak base. To partition in between one or the other, just regular distilled water, you're going to have some weak base go down, you're going to have some weak acid. Any questions on this extraction? So a review of some of our spectroscopy. Here you see a propylamine, and there's two hydrogens. So this broad nitrogen carbon stretch, we see two spikes. Just to review some of the other things, sometimes a little spike over here was an overtone for a carbonyl. That's how the IR spectroscopy looks. Hydrogen nitrogen stretch between 2200 and 3500, right in there. Two peaks for a primary amine, because then you're going to have two hydrogens. A secondary, you're only going to see one peak, and a tertiary, you're not going to have the hydrogen nitrogen bond stretching, of course. So here's propylamine again. Notice here's where your methyl group normally shows up, and it's becoming more deshielded because nitrogen's a little more electronegative than the carbon. We may want to compare this to like if we had an ether here or an alcohol, because nitrogen is not as electronegative as oxygen, so the protons on the alpha carbon are not as strongly deshielded. Is it like 3 to 4? So here's our proton NMR of this. Here's a triplet, this group here being split by those two. And then of course, a big mess. And what's this little peak right here? That's probably these two hydrogens there. And so this mess here is probably these two all bunched together. So one thing I find interesting about carbon-13 NMR is here's the most shielded carbon, here's the most deshielded or least shielded, and that inductive effect you can see traveling all along through there nicely. Mass spectroscopy amines. So we remember the nitrogen rule. Nitrogen has an odd valence and an even mass number. So if we had when we see an even molecular ion, we say it either has an even number of nitrogens, and 0 is an even number. So when there's just like one nitrogen, we're going to see that odd molecular ion peak. When a nitrogen atom is present and you only have one or an odd number, you get an odd molecular weight. So remember that nitrogen rule. So alpha cleavage, this is the alpha carbon, that would be the beta. Alpha's right there, not there. So when that cleaves, you get this alky radical. And so this is electron ionization. We hit this with one electron and two came out. So there's that radical cation here. And this thing can fix things up through resonance. The most common fragment of amines is alpha cleavage. When I copied that in, I didn't get the symbol there. Is alpha cleavage, an inium ion. So when I look at this spectrum, I say, that's odd molecular weight. Could be a nitrogen containing compound. Then of course, I like the integers. 29, that's loss of an ethyl group. That could be alpha cleavage right there, alpha cleavage right there. I'm gonna go 15, 14, and 14. 15, 14, and 14. That's 43. What's 43 from 115? That's 72. So I've rationalized most of the important peaks. Molecular ion peak, base peak, and of course here we see it in detail. Here's alpha cleavage here. That gives us the base peak. Here's the alpha cleavage here, that loss of 29 gives us that 86. Some of this should be a review because which chapter did we just do before this one? The aldehyde and ketone chapter. And there's kind of a table with these different things with the amine, the oxime, the hydrazone, depending on what you got connected to that nitrogen, aldehyde or ketone. And this was a product on exam 3. Hopefully we'll maybe go over that tomorrow. Depends if there's gifts for me in the testing center later today. Aromatic substitutions of aryl amines. So put NH2 on a benzene ring and you have aniline, which is a strong activator. So it's an orthopara director and it's active enough so multiple substitutions is a problem. Protonation of the amine under acidic conditions converts the group into a strong deactivator. Notice that positive charge we put on nitrogen, and then in the sigma complex, putting things in either the ortho or para position, you get a carbocation on the carbon that this nitrogen is attached to, and that's how we rationalized things like carbonyl carbon and the nitro group being meta-directors. So these both occur readily, and we saw this in the benzene chapter, this baking soda to neutralize the acid form. So here's aniline. We're going to put something in the ortho position and here in the para. And of course you can write multiple resonance structures for the pi complex. This looks exciting. Explode. Oxidation of the amino group does interesting things. We're going to look at that in quite a bit of details. Strongly acidic agents protonate the amino group, producing a ammonium salt, and it's strongly deactivating and now meta-allowing. Therefore, strongly acidic reagents are unsuitable for substitutions of anilines. So here's pyridine, it's aromatic, and here are some substitution reactions. And it looks like a meta-director. In regards to the heteroatom. And so notice these are some of the same reagents, using SO3 as an electrophile. Strongly deactivated towards electrophilic attack by the electronegative nitrogen atom. That's why we have the meta position. Substitutes in the third position in a manner analogous to meta substitution. Meta to the heteroatom. And that's because these electrons may react with the electrophile. So here our electrophile hits in the meta position, and we'll never get the positive charge on that, and that's possibly good. So here's the mechanism. Now let's put it in the ortho position. And there you go, no octet, 2, 4, 6. Here I go, 2, 4, 6, 8. I think the octet rule is a real useful thing you learn in general chemistry. So just as we saw with all the meta directors, where we had a carbon here and a positively charged species like a nitrogen or carbonyl carbon, nature doesn't want to put a positive group there. So we don't observe ortho. Of course, they're just calling it the number 2 from the heteroatom. So unfortunately, in the benzene chapter, I decided to keep with the schedule, and I didn't cover nucleophilic substitution, but it's very similar to what we learned in the fall with our other substitution reactions, where here's like a nucleophile and here's like a leaving group. And so this thing can hit here and the electrons move around a little bit. And notice instead of a cation, we have an anion. Eventually those electrons jump off and the chlorine leaves. And so it's a typical substitution reaction, activated toward nucleophilic aromatic substitution. The nucleophile will replace a good leaving group in the number 2 or number 4 position. Ortho or para are analogous to those things. All right, All right, well, we're gonna adjourn early today.